Well, in the second lecture on cardiac function, we'll talk about, start out talking about electrical action within the heart muscle, that is the EKG, and then we'll discuss the sequence of events that are occurring in the different parts of the heart at the same time. So in the electrical conduction system and the mechanical response to that input from the electrical conduction system. So we're going to start integrating material from the first lecture. So electrical activity in the heart can be recorded from electrodes placed on the skin. This is very important because it's a non-invasive technique that allows a great deal of information to be derived about cardiac function, but without having to do anything that is invasive, that is without having to do any sort of surgery or anything that is potentially harmful to the body. And what we're doing with the EKG is we're going to be testing for clinical abnormalities, that is, abnormalities in the electrical conduction system in terms of both the rhythm and the way that the depolarization or repolarization is occurring that may help to explain mechanical problems. So the electrocardiogram, we abbreviate it generally EKG because a German individual by the name of Eindhoven, who we'll be talking about in a moment in another slide, developed this technique. And it's, of course, called the electrocardiogram. And in German, cardio starts with a K, hence the abbreviation EKG. So it's an external measure of electrical activity of the heart, and it looks like this. So the reason that we can get this sort of a recording is that the body is actually an electrical conductor. These various electrical events that we've talked about all semester, nervous system, cardiac system, etc., even muscle, electrical conduction in the muscle, those electrical currents actually travel through the various electrolytes in our body, and therefore electrodes can be placed on the surface of the body and measure these electrical changes. In the EKG, the distance between these different features, the P wave and what we call the QRS complex for existence, as well as the amplitude, that is how high these waves are aspects that are evaluated. And the distance and amplitude depends upon the size of the potentials and how synchronous they are. And of course, that's something that is important in the heart, that we have the appropriate synchronicity. So the heart electrical activity, that is what we call the EKG, is a synchronized discharge of many cells at one time. When we were studying the nervous system, we talked about compound action potentials. And basically, the EKG is a compound action potential being recorded from the heart. Now, the EKG plots voltage, in this case millivolts, because they're small voltages, a recording against time. Now, time is not labeled here, but that this represents a piece of paper that's traveling through EKG machine at a certain rate. Excuse me, at a certain rate of time, generally about a millimeter a second. And this diagram does not show the lines that would normally be printed on EKG paper, but generally there are lines coming down that are spaced about a millimeter apart, so that you can actually use the spacing of those lines as a way of determining the timing of the events. Excuse me. Now, for the purpose of this course, we're not going to be worried about the amplitude of these events. If we were studying a course in pathophysiology or clinical physiology, we would be concerned about the amplitude of these, but we are not going to be. We are interested in the distance between these events, at least to a certain degree, and we'll talk about that. We won't use it as a way of trying to diagnose disease, because again, this is not a course in pathophysiology. But you need to realize that even normal physiological processes can result in certain changes in the distance between these different waveforms. So I mentioned Eindhoven before. Eindhoven was the German physician or physiologist, I'm not actually sure which, that conceived of the idea of recording the electrocardiogram. And one of the major advantages of his technique is he took the approach of, rather than trying to record electrical events in the heart by putting electrodes right over the heart, which are closely spaced, that if you put those electrodes at great distance from each other on the surface of the body, that because these distances allow the dispersion in time of these electrical events, we can actually see these different electrical events separated in time. If the electrodes were all placed together right over the heart, you wouldn't see this separation of the different components of the EKG. You would probably just see something that was a bunch of pen deflections on the EKG machine that were superimposed on each other. So by spreading the electrodes out in a very specific way, it allows the different components of the change in voltage occurring within the heart to be spread out in time. Now, there are actually a total of 12 leads or electrode placements that can be used in the EKG. We're only going to talk about the first 3 leads, and I'm not going to ask you to know these leads specifically. What you're going to need to know is what kind of measurements can be made with them, that is the EKG. But you need to realize that, lead 1, for example, which is this one, always is comparing the left arm with a positive electrode to the right arm with a negative electrode. So an EKG technician has to put the appropriate electrode on the appropriate placement, or the EKG recording is not going to be valid. So the EKG is the electrical activity of the heart. The P wave represents atrial depolarization. So at the very beginning of the P wave is when the SA node is depolarizing. And then as the depolarization travels from the SA node throughout the atrium, it forms the P wave. If you remember, we talked before in previous lecture about the fact that there is a slight delay of about 1/10 of a second in terms of the depolarization moving through the AV node. That is represented here by this flat line, which in fact we call the PR segment. So this represents the AV nodal delay. Then we have depolarization of the ventricle. The QRS complex is ventricular depolarization. And at the same time, we have atrial repolarization. The thing is, of course, that the atrial depolarization is a much larger voltage change than the atrial repolarization. So we see this very large upward deflection. The T wave is ventricular repolarization. Now, this is going to seem a little strange. We've always talked about repolarization as being a hyperpolarization, so you'd expect the T wave to go downward. But you need to keep in mind that we're measuring movement of this voltages through a more or less circular shaped tissue. And that is going to alter how these electrodes, because of their different placements, are being able to sense that movement of charge. So the fact that it's a repolarization, but that it looks like it is an upward deflection. It looks like a depolarization, but it is in fact a repolarization, and that is because the movement of the voltages with regard to the placement of the electrodes. As I said already, the PR segment represents the AV nodal delay. So of course, this period can become longer or shorter, depending upon how much of an AV nodal delay there is. And we'll talk about that a little bit later when we talk about heart block. The next thing is the QT interval. The QT interval is ventricular systole. That is the time period during which the ventricle is contracting. Now again, you might say, well, we have repolarization going on. How can that be going on during the ventricular contraction? You need to keep in mind that these electrical events are much faster and briefer than the mechanical event, that is the contraction that follows it. So if this whole period is ventricular systole, it precedes with ventricular depolarization, but this depolarization is what initiates the action potentials within the contractile cells. And then the contraction itself lasts much longer. In fact, the contraction terminates about here, during which time we already have repolarization going on, but there is still a continued contraction. We saw the same idea back in the skeletal muscle chapter, the idea that the action potential in the muscle cell was much briefer than the actual contraction of the muscle itself, and it's the same principle here. Then we have the TQ segment. Now this is the one that is not shown on your diagram, or at least not labeled, but it is the time between the T wave and the next Q wave. And this represents ventricular diastole. So this is the period of time when the ventricle is relaxed. And then the ST segment, shown here, time between the S wave, which is shown up here, and the beginning of the T wave. This represents phase 2 of the action potential in contractile cells. Remember, phase 2 was the shoulder region on the action potential in the contractile cells. What I'm showing in this lower diagram here is the fact that this is the measured ventricular depolarization, that is a QRS complex. It coincides time-wise with the onset of the action potential in the contractile cells. But as we said a moment ago, that contraction persists until the end of the T wave, and as you can see here, the action potential of the contractile cell, remember this is a muscle action potential, persists for a much longer period of time, and again, as you see, it coincides with the cessation of the T wave. Now, in this case, we're going to put the events from the EKG, which are shown in these panels here, with a graphic representation of the movement of the depolarization through the heart tissue. So here, it's a little hard to see in this diagram because it's smaller, but a small amount of purple showing up here represents the depolarization of the SA node, and it's starting to move through atrial tissue. So this is coincident with the beginning of the P wave. By the time the P wave is ended, as shown here, we have depolarization of all of the atrial tissue. And you need to keep in mind that this also is depolarizing the AV node, which is right here, because of course it's on the floor of the right atrium. So there's a delay between its depolarization and the spread of the depolarization down into the bundle of His. So we have this PQ or PR segment that we talked about before. Then as the depolarization moves down the right and left bundles and starts moving into the Purkinje cells, we see the initiation of the QRS complex. As that depolarization spreads throughout to the ventricles, we see the remainder of the QRS complex showing up. After the QRS complex has occurred, but before the T wave occurs, we have the conclusion of the spreading of the depolarization throughout the ventricle. And now we have some repolarization starting. It is starting on the tissue that was first depolarized, and this is, of course, showing up as the beginning of the T wave. And as the tissue completely repolarizes, we see the conclusion of the T wave, and we're back ready to start again. So the P wave represents atrial systole. It precedes it, but it represents it. The QRS complex represents ventricular systole. During that time, we have atrial diastole, that is, the atrium is relaxing. And after the T wave, we have ventricular diastole as well as atrial diastole, and then again we start out with the initiation of another atrial depolarization and therefore atrial systole. Now you can have disturbances in the EKG. I'm calling it ECG in this slide, but again, same thing as EKG. It can be called arrhythmias. Many sources call them dysrhythmias. I myself prefer the term dysrhythmia because it suggests a dysfunction in the rhythm. And technically, arrhythmia suggests a lack of rhythm, which of course would mean that there is no rhythmic change in voltage. Therefore, basically we call a flatline EKG, which is consistent with death. We're showing here a normal EKG. The T wave's a little larger than we saw in the previous diagram, but it may represent a different lead placement than what we had before. And in this case, these are not really disturbances. They represent abnormal rates, that is, deviations from normal heart rate. So we have what we call sinus tachycardia. Tachycardia means high heart rate. Or sinus bradycardia. Bradycardia means slower heart rate. The sinus part of the name refers to the sinoatrial node, or the sinus. So in this case, heart rate is faster, and therefore the EKG is different because the sinoatrial node is depolarizing faster. So of course that is consistent with a higher heart rate, or tachycardia. So what we see here, if this is the normal interval that we should be getting, roughly 1 second, as you see here in the time scale, between the QRS complexes, that would be consistent with a beat or a rate of 60 beats per minute. Here we have almost 2 full cardiac cycles occurring in that same period of time. So in this case, the heart rate might be something like close to 120 beats per minute. It is not itself truly an abnormal EKG. It just represents the fact that the heart's beating faster. And with that, the shape of the P wave seems a little smaller. The T wave seems to be inverted some, but none of that is indicative of any pathological event. And sinus bradycardia would represent, for example, increased parasympathetic activity, slowing the heart, whereas sinus tachycardia would indicate increased sympathetic activity, increasing heart rate. So we have increased parasympathetic discharge, and what we see is this period between QRS complexes is longer than the normal period. So in this case, maybe heart rate is dropped down to about 45 beats per minute. So you can actually use an EKG, especially in a real one where you have the time markings here on the paper, to determine heart rate. But also, you can look for whether or not there are disturbances in the waveforms. And we're going to see some of those disturbances now. So first-degree heart block. What we have is slowed conduction through the AV node. Now remember we talked about before, it takes about 1/10 of a second for the depolarization to move through the AV node. In first-degree heart block, it actually takes longer. And that is shown here by the fact that this PR interval is much longer here than it is in the upper tracing. So it's taking more time for this depolarization that starts in the P wave to get through and depolarize the ventricle. This is called first-degree heart block, and it is just simply slowing conduction through the AV node. It increases the duration of the PR segment. It itself is not particularly pathological. Excuse me. If it gets worse, it can progress into second-degree heart block. Second-degree heart block, we can have slowed or sometimes stopped conduction through the AV node. So again, we have our normal EKG here. And of course, you have a P wave followed by a QRS complex, a P wave followed by a QRS complex, etc. In second-degree heart block, you can see something like this. You have a P wave with a QRS, a P wave without a QRS, another P wave without a QRS, a P wave with a QRS. So in normal EKG, you always have a 1-to-1 ratio in terms of between the occurrence of the P wave and the QRS complex. In second degree, you can have a 2-to-1, as we have here. 2 P waves without a QRS, and then 1 with. So this would be a 2-to-1 rhythm. It can get to be 3-to-1, etc., but it generally is some sort of an n-to-1 rhythm, that we have actually some number that is persistent. So for long periods of time, you see a 2-to-1 rhythm or a 3-to-1 rhythm. This could be caused by a variety of things. One of the main things is increased parasympathetic nervous system activity, actually suppressing the depolarization of the AV node enough to stop conduction through it. It can progress and become worse, moving to what we call third degree or complete heart block. Again, we have our normal EKG. Here's 2 different examples of third degree heart block. In this case, if you notice, here we have a QRS complex, a T wave, then a P wave. No QRS complex. This P wave occurs pretty much during the QRS complex. This one precedes it. If you notice, even though you could say, well, it's a 1-to-1 association, that the timing of the P wave and the QRS are completely random with respect to each other. And down here, it's even worse. The P wave has absolutely no relationship to the QRS complex. So in this case, we have a loss of conduction through the AV node. The atrium is depolarizing on its own and contracting on its own, and the ventricle is doing the same. So the depolarizations and contractions of the atria and the ventricle are completely independent of each other. This, of course, means that the atria are not helping to fill the ventricles, and therefore the ventricles are not pumping as efficiently as they could. Now this diagram, the Wiggers diagram, is the single most important diagram for cardiac physiology. Now, that doesn't mean it's the only one you need to know by any means, but it puts everything together. We have the EKG. We also have the upper waveform here. Perhaps I should just trace this waveform here, which is the aortic pressure waveform. And you should probably use the Wiggers diagram in your book as we go through this particular slide on the lecture, because it's going to be easier to see it in the book than it is on the reduced size of this presentation. We have the ventricular pressure wave. This is the left ventricle. We have the atrial pressure wave here. And we have heart sounds shown. Heart sounds represent the closure of valves. And we have left ventricular volume. So this graphic portion is the true Wiggers diagram. This particular illustration I'm using then superimposes a diagram of the heart and what's happening, so that you can actually see the events in the heart muscle itself and how it corresponds to these events in the diagram. So we'll go through it. First of all, I want to point out again, I have in a previous lecture, that there is this website that has an excellent animated version of the Wiggers diagram, which I think is even easier to comprehend when you actually see it moving. So let's go through it one at a time. We have our P wave in the EKG. The P wave in the EKG is leading to atrial systole. So we have the P wave, atrial systole. Atrial pressure here, it's a little blue line, goes up a little. It doesn't go up much. The atrium is very small, but here we have the atria contracting. That is not only increasing atrial pressure, but you notice the line right below it, ventricular pressure is going up as well, because we're pushing more blood into the ventricle. Then we have our QRS complex. So the ventricle starts contracting. Ventricle starts contracting, the ventricular pressure starts rising rapidly. This closes the AV valve, so we see this noise that's associated with the closure. Pressure during this time in the ventricle is not changing. Before that, it was increasing because the atrium was contracting, pushing blood in. This is what's called, this particular phase right here, it's a very narrow area, isovolumetric ventricular contraction. The ventricle is contracting and blood will not leave the ventricle until the pressure in the ventricle equals the aortic pressure. As soon as it starts exceeding the aortic pressure, of course, the pressure in the ventricle is now above that of the aorta, it will eject the blood, push the blood out. And of course, aortic pressure will go up as well because the blood is being pushed into the aorta. Now notice this is occurring during the time period between the QRS complex and the peak of the T wave, and certainly before the end of the T wave. So this is what we call ventricular ejection or ventricular systole. Atrial pressure goes up initially because as the ventricle contracts, it's pushing against the wall between the atria and the ventricle, so it's pushing some pressure in. But then, of course, the pressure goes down because the blood is now ejecting out into the aorta. Ventricular pressure continues to go up until, and because as the muscle, of course, is shortening, it's producing less and less pressure after this peak value is reached. And at some point, ventricular pressure drops below aortic pressure, in which case the semilunar valves close. We have heart sound number 2. Ventricular pressure continues to come down. Atrial pressure is going up here, of course, because there's blood coming into the atrium. This period here is called isovolumetric ventricular relaxation. If you notice, as ventricular pressure is going up, ventricular volume is going down. It makes sense because this blood is being ejected out into the aorta. And it stays, ventricular volume stays unchanged here, or largely unchanged, because we're still having some relaxation going. When the ventricle has finally relaxed, blood is moving from the aorta in, the atrium in. So the atrial pressure is now going down, but the ventricular volume is going up because the blood is moving from the atrium down into the ventricle. And of course, then ventricular pressure is going to go up as ventricular volume does, and going along with atrial pressure because it's blood coming into the atrium, moving down into the ventricle. Then we have again going on here to the right, but I'll show it here on the left. Then we're going to have another atrial systole, atrial contraction, pushing more blood into the ventricle. So the value of the Wiggers diagram is to look at all of the different events, the electrical events, the mechanical events, the changes in volume, the changes in pressure in the different chambers of the heart that are going on at the same time. And it helps to illustrate the movement of blood from chamber to chamber. So this is something that you really should study very thoroughly. I don't want to say commit it to memory. It's hard to memorize a diagram. But challenge yourself. Point at something. What's happening here? What's happening here? What's happening here? And by doing that, you'll have a much better idea of what cardiac function is. So now we're going to sort of dissect out some of this and some of the details. So the opening of the valves during the cardiac cycle. Remember, the valves open passively due to pressure gradients. The AV valves open when the pressure in the atria exceeds the pressure in the ventricles. The semilunar valves open when the pressure in the ventricles exceeds the pressure in the arteries. They then close when ventricular pressure exceeds atrial pressure, or when the arterial pressure exceeds the ventricular pressure. So it's pressure changes on either side of the valve that's causing them to open or close. So let's look at ventricular systole. This is again a Wiggers diagram. It's just breaking it down into little pieces. So let's take a look at isoventricular, isovolumic, or isovolumetric, both terms are used, ventricular contraction. Now, this particular diagram is using labels that we're calling phases. This is not necessarily a standard usage. But phase 2, we're enumerating with phase 2 up here, is what we call isovolumetric ventricular contraction. So you have ventricular pressure going up. It's going up once it matches aortic pressure. Of course, the AV valve and aortic valves are closed until that time. But as soon as those valves open, we have ventricular ejection. So blood is now being pushed from the ventricle into the aorta. So ventricular pressure is going up, aortic pressure is going up as well because the ventricle is pushing the blood into it. And of course, as the muscle is contracting, it's going to get to the point where it's developing less tension, less pressure, so the pressure is going to peak. And the two pressures, that is ventricular pressure and aortic pressure, will decline. And then we're going to have closure of the aortic valve. At this point, aortic pressure actually goes up some because of the elastic recoil of that valve closing sort of pressurizes the blood in the aorta for a moment. So what's called the dicrotic notch. And then from that point on, the ventricular pressure is going down because the muscle is continuing to relax. So that was ventricular systole. Now let's take a look at ventricular diastole. So ventricular diastole starts right here as soon as the aortic valve closes. So starting right here. And the ventricle is relaxing, which of course is what ventricular diastole refers to. Ventricular relaxes so that the pressure in it is lower than that of the aorta. And then comes down, and then we start ventricular filling. At this point, blood that has been accumulating in the atrium is now going to start draining into the ventricle. So atrial pressure will decline, but then start going back up along with ventricular pressure, and that's going up just because of the accumulation of blood in the ventricle. Let's take a look at the ventricular volume curve. We have the end diastolic volume, which is the volume of blood in the ventricle at the end of diastole, hence end diastolic volume. So this is the amount of blood that's available to the ventricle to eject during ventricular contraction. Then we have end systolic volume, which is the volume of blood remaining in the ventricle after the contraction. As you see here, you start out with about 120 milliliters, and you end up with about 60. So as I said before, the ventricle does not eject all of the blood that's in it. It ejects about half of the amount of blood. And again, that goes back to the idea of the length-tension relationship we talked about in skeletal muscle. That the muscle, once it starts shortening, it can only shorten so much, and after that it's going to lose tension. So it's not going to be able to shorten or contract enough to eject all of the blood from the ventricle. So with that, we have what we call a stroke volume. That is the volume of blood that is ejected each time the heart contracts, or during each stroke. And it is calculated by taking the end diastolic volume and subtracting the end systolic volume. Taking the end diastolic volume and subtracting the end systolic volume. This amount of blood ejected during each contraction of the ventricle. Which leads us to the concept of ejection fraction. What fraction of the end diastolic volume was ejected? So it's the fraction of the end diastolic volume that is ejected during a heartbeat or during a cardiac contraction. It is the stroke volume divided by the end diastolic volume. And in the previous diagram, it would have been 50%. That was just for illustrative purposes. Typically, you would have a end diastolic volume of about 130 mils, depends upon the individual and the size of their heart, clearly, and an end systolic volume of about 70 mils, giving you about 54%. So the typical textbook value is 55% is the normal ejection fraction. Now, during the cardiac cycle, there is continuous blood flow, even though the heart is contracting in a rhythmic way, which gives a certain pulsatility, which is why we talk about blood pressures being 120 over 80. It never goes down to zero, at least in the vascular system itself, but it goes up and down during each contraction of the heart. But the blood flow is still continuous throughout the system. And that is because the aorta and other large arteries are very elastic, so they act as a pressure reservoir. So let's go back to one of the Wigger diagrams here. So we have pressure coming into the aorta here, and then the valve closes. We have this dicrotic notch, and there's a fair amount of pressure here. If you notice, it continues to decline, but it's still well above ventricular pressure. And this pressure stays up there because of this elasticity of these large vessels. So they're being stretched out as blood is being pushed into the aorta, and then they slowly recoil, and that is helping to keep pressure up. So we're storing energy during systole as the walls of these vessels expand, and the released energy during diastole as the walls recoil inward maintains blood flow through the entire cardiac cycle. So even though blood pressure does go up and down, it goes up and down between 120 millimeters of mercury and 80, rather than 120 and 0. Let's talk briefly about the heart sounds. Heart sounds are due to turbulence that is caused when the valves are closing. Now, we generally refer to as the sound of the heart. If you just listen to somebody's heart through a stethoscope, as sort of a lub-dub. So the first heart sound is what we refer to as the lub. The second heart sound is what we refer to as the dub. The reason we have the D beginning of it is that it's a harsher sound, and it's because the sound is actually louder. So the first heart sound is when the AV valves are closing simultaneously. And of course, that's happening under somewhat lower pressure than during the second sound when the semilunar valves close simultaneously. So this sound, the dub, is louder than the first sound, the lub. These sounds can change with pathological conditions, and in fact, there are two other heart sounds that only show up during pathological conditions. And those are topics that you will study in much greater detail in other courses and later on in your programs. Excuse me. So let's look at the concept of cardiac output. It is the volume of blood pumped out by the ventricle per minute. So it is the stroke volume times the heart rate. And we're much more interested in the amount being pumped per minute than the amount pumped per cycle, because, of course, this is what's meeting the minute-to-minute demands of your body. Average cardiac output is about 5 liters per minute at rest. The average amount of blood volume in your entire circulatory system is 5.5 liters. So in 1 minute, almost all of the blood in your entire cardiovascular system is circulated throughout the system and is pumped through the heart. It is regulated. Both heart rate and stroke volume are regulated, and they are regulated by both extrinsic and intrinsic means. Extrinsic means include neural, that is autonomic nervous system, and hormonal. Intrinsic means are autoregulatory aspects of how the heart functions. So one thing is We've already talked about this idea of the length-tension relationship in skeletal muscle, and I keep referring to it as applying to cardiac muscle, and it's an intrinsic aspect of control that actually controls cardiac output. So we'll talk about that in a moment. Extrinsic control, autonomic inputs. You have the sympathetic and the parasympathetic input to the heart. If you have here this tracing referring to your SA node pacemaker potential, and this is what's happening at rest, if the sympathetic nervous system is activated, what you see is this depolarization speeding up. So the sympathetic nervous system speeds up the development of the pacemaker potential. It increases heart rate. We refer to this as a positive chronotropic effect. If you take a look at what's happening, the slope of both our funny current as well as the T-type calcium channel depolarization, the slope of this line is steeper than at rest. So we actually have more charge moving through the membrane more rapidly when the sympathetic nervous system is activated. And if you take a look here at the bottom of the repolarization phase normally versus what's happening in the sympathetic nervous system, that the cells do not become as hyperpolarized. Now when the parasympathetic nervous system is activated, here's again our control wave. When the parasympathetic nervous system becomes activated, it slows the pacemaker potential. The shape of it, the peak of it, for either system remains the same. But what we have here is that the repolarization phase brings us to a more hyperpolarized state when the parasympathetic nervous system is activated. And if you notice, the slope of this pacemaker potential is the same as we saw at rest. So we're not actually moving charge through at a different rate, but when we repolarize, the cells are more hyperpolarized, so it takes longer for the pacemaker potential to bring the cells to threshold. So we're slowing heart rate, slowing the depolarization. This is called a negative chronotropic effect. If you take a look at the muscle tension, that is how much the muscle contracts, when the sympathetic nervous system is activated, the muscle develops more force, more tension than it does at rest. Now that's the sympathetic nervous system. The parasympathetic nervous system does not affect contractility of the heart. It does not affect muscle tension in the heart. So heart rate is determined by the SA node firing rate, the rate of depolarization. Its intrinsic rate, as we talked about in a previous lecture, is about 100 beats per minute, meaning that without any input from the autonomic nervous system, your heart rate would be 100 beats per minute. But your SA node is under the control of the autonomic nervous system as well as hormones. That's primarily the autonomic nervous system under most circumstances. So at rest, as you're sitting here listening to this lecture, your heart rate is probably as high as 75, maybe even lower down to 60, indicating that you have parasympathetic activity dominating and bringing the heart rate down from its intrinsic rate. During excitement, sympathetic nervous system takes over and the heart rate increases. But it's only when your heart rate goes over 100 that it's actually being driven to that rate by the sympathetic nervous system. Otherwise, it's a reduction in the activity of the parasympathetic nervous system. So the sympathetic nervous system increases sympathetic nerve activity by releasing norepinephrine as well as epinephrine coming from the adrenal gland. This activates beta-1 receptors in the SA node. This increases the open state of the funny channels as well as the T-type calcium channels. That is what causes this line, this pacemaker potential, to have a higher slope, to rise more rapidly than what we see normally. because we have this increased opening of the funny channels and the calcium channels. And then this, of course, is going to increase the rate of the spontaneous depolarization. It's going to make these depolarizations occur more rapidly than they normally do, and increase heart rate. So let's take a look at how this happens. So we have norepinephrine or epinephrine binding to beta-1 receptors. Beta-1 receptors are coupled to the GS protein. Remember, GS stimulates adenylate cyclase, converting ATP to cyclic AMP. So we have an increase in the amount of cyclic AMP being produced. That is going to activate more protein kinase, which is going to open up the funny channel, allowing more sodium in, as well as open the T-type calcium channel, allowing more calcium in. And of course, those two ions together coming in more rapidly is going to produce a more rapid depolarization. Let's take a look at the effects of the parasympathetic nervous system. So the vagus nerve is the parasympathetic nerve coming into the heart. Parasympathetic nervous system, of course, releases acetylcholine, which at target tissues binds to muscarinic receptors, and in this case, in the SA node. Those muscarinic receptors are going to increase the open state of potassium channels and the closed state of calcium channels. Now, if you think about it, if you have increased opening of potassium channels, more positive charge can leave the intracellular fluid. So it's going to become more hyperpolarized. And you're increasing the closure of the calcium channels, which is going to stop positive charge from coming in. So it decreases the rate of the spontaneous depolarization and ultimately will result in a hyperpolarization of the cell. And we talked about that. Here we have a more hyperpolarized membrane than we had here, so it's going to take longer for it to become depolarized, and that is going to decrease heart rate. Let's take a look at the molecular events. Acetylcholine binds to the muscarinic cholinergic receptor, and there are two G proteins that are associated with the muscarinic receptor, one of which is going to close the T-type calcium channel, so of course stopping calcium from coming in. So we're inhibiting channel opening. The other is going to increase the opening of potassium channels, allowing more potassium to leave, causing a net hyperpolarization. So the AV node, we've been talking about the SA node. The AV node also is innervated by both sympathetic and parasympathetic nervous system. The sympathetic nervous system increases the conduction velocity through the node. So we said there's normally a nodal delay of about 1/10 of a second. So if the sympathetic nervous system gets activated, it becomes less than 1/10 of a second. When the parasympathetic nervous system gets activated, it decreases the conduction velocity through it so that it would take more than 1/10 of a second, perhaps as much as 2/10 of a second. Hormonal control of the heart. Well, epinephrine is the hormonal arm, if you will, of the sympathetic nervous system, and it has the same effects as the sympathetic nervous system itself. Glucagon increases heart rate, and glucagon is a hormone that we'll talk about in several more chapters from now when we talk about endocrine control of metabolism. But glucagon is basically involved in energy regulation. Other factors that can affect cardiac output. Well, the stroke volume. We've talked about that already. Main factors that affect stroke volume are the ventricular contractility, that is how forcefully the ventricle contracts, the volume that you start with, so the end diastolic volume, and then the afterload. Afterload is related to blood pressure. Specifically, the pressure within the aorta. Remember, blood doesn't start leaving the ventricle until the ventricular pressure starts to exceed the aortic pressure. And that's the idea of afterload. So stroke volume will affect cardiac output. Ventricles never completely empty of blood. That's why we have our ejection fraction, remember? But a more forceful contraction will expel more blood. So we've already said that the sympathetic nervous system will give us a more forceful contraction. And ejection fraction will increase to something greater than 54%. It may go up to 60, 70, 75%. It never goes to 100%. This can be changed, again, by extrinsic factors. We've already talked about sympathetic input, or as well as hormonal input. But then the intrinsic control, changes in the end diastolic volume. Well, those are related to what we call venous return, that is how much blood is coming back from the veins to the heart, and with that, the amount of stretch of the ventricular tissue, which is what we refer to as the Starling law of the heart. So let's take a greater detailed look at that. Sympathetic innervation of contractile cells. You have the cardiac nerves, just as we've seen before for rate. Norepinephrine binds to beta-1 receptors and increases the contractility, increases the force that the cardiac muscles develop. Parasympathetic input does not have any significant effect on stroke volume. Thyroid hormones, insulin and glucagon, all can increase the force of contraction. All of these are related to energy metabolism. So it makes sense since the cardiovascular system is providing energy to the rest of the body by sending blood-borne calories and nutrients, that having hormones that are involved in regulating energy metabolism would, in fact, be able to affect the output of the heart. So sympathetic effects on contractility. We're basically going to increase calcium at the beginning of contraction. So we have norepinephrine or epinephrine binding to beta-1 receptors, stimulating GS. This is just like we saw before in terms of rate. Increasing the amount of cyclic AMP available, and that's doing several things. It can be, again, protein kinase can be actually phosphorylating regulatory proteins that are associated with actin. It can open up the L-type calcium channels, allowing more calcium to come in. It can increase the activation of calcium channels to make them more sensitive to the depolarization. And it can increase the rate of the calcium ATPase. This is, again, our SERCA, the sarcoplasmic reticulum calcium pump, pumping calcium back in. And this is, of course, going to be important from a standpoint that if you want greater contractility, you do want more calcium availability, but you have to get rid of that increased calcium before the next cardiac contraction so that you have can produce a greater change due to this input from calcium. So you also need to pump the calcium back into the sarcoplasmic reticulum faster at the end of the contraction. So protein kinase A is going to trigger calcium release from the sarcoplasmic reticulum. It's going to increase the rate of contraction and peak force. This is referred to as the positive inotropic effect. And notice it is not spelled I-O-N-O. It is I-N-O. It is not ionotropic. It is inotropic. This refers to force of contraction. And decreased availability at the end of calcium at the end of contraction by working on the SERCA pump. So we have faster relaxation. This is called a positive lusotropic effect. So everything we've talked about so far is extrinsic control of stroke volume. Now we're going to talk about intrinsic control. Now the Frank-Starling law, or sometimes called the Starling law of the heart, is an intrinsic mechanism. It is related to the length-tension relationship that we've already discussed in terms of the skeletal muscle. The thing is that since the heart is not a linear type of muscle, the way skeletal muscle is, but it's circular, rather than talking about a length-tension relationship, we talk about an end diastolic volume-stroke volume relationship. But if you think about it, as end diastolic volume goes up, length of individual muscle cells is being increased. And increasing stroke volume is the same as increasing tension. So it is a length-tension relationship as well. So as we bring more blood into the ventricle, we stretch our sarcomeres out. But again, there is an optimum length in skeletal muscle, so there is an optimum volume in cardiac, in terms of cardiac function. If we stretch it too much, the tension starts dropping off. If we contract it too much, the tension starts dropping off. So we actually want to be right here in this optimum range. So increased venous return, that is increased blood flow into the ventricle, is going to increase stroke volume up to a certain point. This curve is going to flatten out very quickly beyond what's shown in this curve. So the increased end diastolic volume stretches the muscle fibers, and this is going to bring them closer to optimum length, going to give greater strength of contraction. And the result is that a small change in volume coming in produces a bigger amount of stroke volume going out up to a certain point. If you increase sympathetic nerve activity, this curve actually shifts upward, meaning that for a given end diastolic volume, you end up with a larger volume than you would have had otherwise. Or if you decrease sympathetic activity, because remember, parasympathetic activity does not affect contractility. So if you decrease sympathetic activity from this level down here for the same end diastolic volume, you end up with a lower stroke volume than what you would have had initially. So the extrinsic and intrinsic mechanisms that affect contractility do interact. Now, factors that affect end diastolic volume, because end diastolic volume affects stroke volume, so we need to be concerned about factors that affect end diastolic volume. Filling time. Higher heart rate means there is shorter filling time. If there's less time for blood to come into the ventricle, we have a smaller end diastolic volume and a lower stretch on muscle fibers. Heart rate is slower, we have a longer filling time, therefore we're likely to have a larger end diastolic volume and more stretch on the muscle fibers. Atrial pressure, that clearly, we've already talked about that, but we'll review it again. Greater atrial pressure increases end diastolic volume because, of course, it's pushing more blood into the ventricle, which produces more stretch on the muscle fibers. Smaller atrial pressure produces a smaller end diastolic volume, therefore a lower stretch. What's called central venous pressure. This is the pressure in the large veins that lead to the heart, and it directly affects both filling time and atrial pressure. And then afterload is the pressure in the aorta during the ejection. So greater aortic pressure means less ejection and greater end diastolic volume. Lower or smaller aortic pressure produces greater ejection and a smaller end diastolic volume. And you need to appreciate how those things can interact with this curve. A greater volume is going to produce, going from here to here, it's going to give you a greater stroke volume. The same volume change coming up here is going to increase stroke volume, but as you go up higher, same volume change is going to have a smaller increase in stroke volume because you're stretching the muscle too much. So when you talk about these factors, You don't want atrial pressure and end diastolic volume to get too large. You don't want it to get too large, nor do you want it to get too small. If it is too low, it's going to decrease your stroke volume. So it has to be maintained in some optimum range.